So we take a look at our homework question that was left on the board yesterday at the end of class, where we had five vectors drawn at funny angles. What's the first thing that should come to mind when we see this drawing? I hate funny angles. Okay, if you think that's stupid to say that, to think that, good, because the stupider it is, the more likely you are to remember it. Okay? In the end, I don't care what exactly you say or what exactly you think, but the first thing that I want you to spot is the fact that we have funny angles and we don't want them. Okay? Regardless of what kind of silly expression you use, we don't want those funny angles. So let's get rid of them. Let's redraw both of those funny angles over here. Don't try to do it on the picture. It becomes too cluttered if you do it on the diagram that we already have. Do it off to the side. Okay, we have 30 degrees right here. This is, what was that? Didn't draw that one in. John, what was this one? How long was this? 100 meters. So we got a 100-meter hypotenuse. This is our x component. This is our y component. Which side of the triangle is the 100 meters? Opposite, adjacent, or hypotenuse? It's hypotenuse, right? Which side of the triangle, Eric, is the x side? Opposite, adjacent? Good. And which side is the y side? Which side is the y side, Tyler? Good. So we're going to use, because the x component is the adjacent side, we have the hypotenuse. Let's use cosine for x. Now, to solve this, we're just going to take the 100 up and say 100 times cosine 30. That ends up being equal to 86.6 meters. The y component we're going to find by the sine function, because it's the opposite side. Y ends up being equal to 50 meters. So what we can do, if we want to, and I know for a lot of people this is helpful, maybe not for everybody, but what we can do is replace that with an x component that's 86.6 and with a y component that's 50. Now we still have one more funny angle that we got to deal with though. That's this 25 meters down here. And this one seemed to be the one that was giving people a little bit of trouble yesterday before we left. We draw this 25 meter angle, or this 25 meter vector. We have a 60-degree angle here. People are trying to draw 50 meters here. Is that what we want to do? Do we want to draw that 50 meters there? These two vectors have nothing to do with each other. Okay, you walk east, then you walk north. The fact that you're walking north has nothing to do with the fact that you just walked east. So I don't care when I'm going 25 meters at 60 degrees. I don't care what I did in the last stage. I care what I'm doing now. Okay, what am I doing now? I'm going at 25 meters at 60 degrees. We're going to measure that relative to an axis, not measure it relative to another vector. Does that make sense? Now it happens to be, that other vector happens to be on the same axis, but that's purely coincidental. Doesn't matter. Okay, always measure it relative to an axis, either an x or a y. In this case, it's measured relative to the y-axis. That means x is the opposite side and y is the adjacent side this time. So we're going to say sine 60 degrees is equal to opposite over 25, the hypotenuse. 25 times sine 60 is what? John, you have that? 21.65. Thank you. Let's do the y component, which is the cosine function. Notice in the last one, right, x was cos, y was sine. In this one, y is cos and x is sine. Okay, it just depends upon where the angle is. This is going to give us 12.5 meters. So what I can do right here if I want to is replace that 25 meters with a 12.5 meters and, a 21.65 meters along the x-axis and a 12.5 meters up. Now I've got a diagram that has no funny angles except for the red one, the resultant one, which that's okay because that's the one I'm trying to find here. Now it should be a lot simpler. Okay, so now let's break the whole thing down into our x's and our y's. The x component of the first one. Spencer, the x component of the first one is what? Yeah, negative 200. Good. Negative because it's to the left. The x component of the second one, Joe? 50? 0. The y component is 50, right? Okay, the x component is 0 because it's on the y-axis. We want the x-axis. The third one, the x component of the third one. 86.6, positive because it's to the right. The x component of the fourth one is 0. The fifth one is 0. The sixth one is 21.65. We need to add those up. What do we get when we do add those up? Negative 91.75. Thank you. Now let's do the y components. The y component of the first one, Jeff, is what? Good. The y component of the second one, Joe, I think it was, it said that? 50 or negative 50 because it's down. The y component of the third one. Y component of the third one, Kathleen. Just look at it here. The y component of this one right here. Right. The y component of the fourth one, Tara. Good. Neg 50 of the fifth one. Ryan, the fifth one is, y component is, no, the y component is negative 50. And the y component of the sixth one is what, Oliver? 0. This one's easier to add up. We get negative 150. Did I forget one? Oh, I did. Did I forget the 12.5 on the other one too? Oh, but it's a y component, right? So it was, we added a 0 on the end of that one, right? We added 12.5 onto the end of this one. You're right. Thank you. A little bit harder to add up, but still not too bad. Negative 150, negative 137.5. Okay, let's combine these now. 91.75 to the left. 137.5 down. Because remember, the goal is to get a right angle triangle, right? I didn't have a right angle triangle. Once I did this stuff over here, I got right angles, but it's still a lot of vectors there. It's still not a triangle. This is what I'm doing to get it into a triangle. And now I've got it in a triangle. My resultant will once again be drawn from start to finish. And I'm going to find my resultant by saying the square root of 91.75 squared plus 137.5 squared. And what was that, 156? 165? Does that make sense? What about the angle? Always drawn at the start of the diagram. The angle, remember, is the inverse tan, the second function on your calculator, second function tan of opposite over adjacent of 137.5 divided by 91.75. If there's a negative in there, drop it now. Okay, 56 degrees. And we know that we went west, then we went south. We went south after west or south of west. Okay, hands up if you got 165 at 56 degrees south of west. Okay. How many people didn't get the right answer, but know exactly where they made the mistake and know exactly what to do here now? Okay, where was it? Where was the mistake?
I guess it was on my calculator because I got 91.75.
Okay. Okay, so you got these numbers, and then it was just a matter right here. Okay, okay. That's important, obviously, but it's probably the least important part of it. So if you do that, then you're still probably going to get a 4 to 5 on the question. Still get a good mark on it. Jazzy? Oh, okay. You did the same thing as I did. I forgot the 12.5 until somebody reminded me to do that. We're good at that? Good enough to have a little quiz tomorrow on this stuff? It's been a while since we've had a quiz, eh? We gotta have another one tomorrow, okay? The quiz tomorrow will basically be just this, right? Just a question where you have, 3 or 4 vectors. You gotta add them together. You'll see a funny angle in there, maybe even a couple funny angles in there, okay? But no tricks to it. Okay, it won't be any harder than what we just did here just now. Okay, if you got this, you should get 100 on tomorrow's quiz, right? Make sense? All right. Here's what I'm going to assign as homework for tomorrow. the vector walk you did the other day. Okay, I want you to find your displacement. In other words, add those vectors together. Okay, if you walked this way, and then you walked this way at 30 degrees, and then you walked this way, or whatever, okay, I want you to find your displacement, which is add those vectors together. Okay? So it's exactly the same thing as we just did, except this time you're using real data. If you can't make out your diagram, if you're having trouble figuring out what the angles should have been, don't panic about that. Okay, just do your best. If your diagram is slightly off, your original diagram is slightly off, and your angles are slightly wrong, it's not the end of the world, because the main point of this is just the exercise of analyzing it. Okay, so we're not gonna take this in for marks. It's just going to be, are you done? Okay, do you understand what you're doing? Okay, good. Okay, I got a few questions for you here before we show you anything else on the board. Let's see, who's a baseball player here? We don't have, yeah, Javi is, yeah. Javi's not here today. Don't have any real big baseball players, I guess, here now. Let's say that we did. Let's say Javi. What position does Javi play? Does he pitch? Okay, so let's say Javi is pitching. Let's say he's the Dogs are going on a trip to Arizona in the middle of the winter when it's -20 in Okotoks, when it's +25 in Phoenix, and let's say they're going to play in a baseball tournament down there and represent Okotoks. Say they're on the airplane and guys get horsing around a little bit. Javi says, "Oh, well, look, it's getting close to game time. I better start warming up." Now, I wouldn't recommend ever doing this on an airplane, okay? Your airplane is traveling at 800 kilometers per hour to the south from Calgary to Phoenix. Javi decides he's got to start warming up. So he decides he's going to throw a baseball at 100 kilometers per hour while on the airplane. Okay, again, I don't recommend this. But he decides he's going to throw it at 100 kilometers per hour to the north. What's the velocity of the baseball? Okay, Javi's throwing the baseball at 100 kilometers per hour north, and the airplane is moving on relative to the ground at 800 kilometers per hour south. What's the velocity of the baseball? 700 to the south? Okay. Who agrees with that? Who doesn't agree with that? Who says something else? So 2 people commit to this. Boy, you guys are fence sitters. You could be right, but somebody else that gives me a different answer could also be right. What's the velocity of the baseball? Could be 700. What else could it be? 100. Javi threw it at 100, right? Which is right. You're both right. How can you have 2 correct answers? It all depends upon what you're defining the motion of the baseball relative to. If it's relative to the airplane, how fast is the baseball moving? 100. If it's relative to the ground, how fast is the baseball moving? 700 kilometers per hour to the south. That make sense? Okay, let's say sometimes me and my son, we get bored at the mall quite easily. Get bored when we're out shopping pretty easily. So sometimes we try little things to keep us entertained at the mall, like running up the down escalator and running down the up escalator and racing each other on the escalator, opposite escalators, and so on. Let's say you ever done that? You ever ran up the down escalator? Everybody's done it. No? No? You should try it. Let's say I'm running up the down escalator. The down escalator is moving at 3 meters per second down. I'm moving at 3 meters per second up. What's my velocity? 0? Who says 0? Relative to what? Right? Relative to what? 0 is a correct answer. Relative to the ground. What's my velocity, though, relative to the escalator? 3 meters per second up the escalator, right? Relative motion always has to have a frame of reference. You always have to define motion relative to something. Now, in all the questions that we've done to this point, we have we have defined the motion relative to something. We haven't necessarily thought of this every single time we've done a question, but in the end, by process of omission, by not really defining it relative to something, we, by default, did define it relative to the Earth. Okay, you're driving a car down the highway, 100 kilometers per hour. That velocity we assumed was relative to the Earth, right? Well, what if you're on the back of a truck? Well, you probably wouldn't drive it at 100 kilometers per hour on the back of a truck. But let's say you're driving it at 4 kilometers per hour and it's on the back of one of those semi-trucks. Well, then we've got to pick our frame of reference, either the Earth or the semi-truck. It's always relative to something. And we can have two correct answers depending upon what we make it relative to. Okay, all the questions that we've done so far, relative to the Earth. But if we had to define them relative to the moon, we would have gotten a completely different answer, but also a completely correct answer for that frame of reference. Got it? Make sense? All right. Today we're going to talk about that in two dimensions actually. But before we do that, I'm going to have you write something down about the airplane here. The airplane is traveling at 800 kilometers per hour east. When a baseball is thrown inside of it at 100 kilometers per hour, the relative velocity of the baseball is, what could it be here? 700 kilometers per hour. What else could it be? Sorry? Could be 100 kilometers per hour. What else could it be in this question? 900 kilometers per hour, because we didn't say which way we threw the baseball, whether we threw the baseball to the east or the west. So there could be three correct answers there. One, a couple answers depending upon the frame of reference, a couple answers depending upon which way we threw the baseball. When we determined all of those numbers, we added vectors together. If we were trying to find the velocity of the baseball relative to the ground, and the baseball was moving to the east, then we would have said 800 to the east plus 100 to the east gives us 900 to the east. If we said, look, the baseball was moving to the west, then 800 to the east plus 100 to the west would give us a resultant vector or a sum of 700 kilometers per hour to the east. When we wanted to find the relative velocity, we added vectors together. When we want to find relative velocity in two dimensions, and maybe this time the airplane is traveling at 800 this way, but we're throwing the ball this way, perpendicular to the way it's moving. We want to find the relative velocity in two dimensions. We've still got to add vectors together, but we're adding vectors together in two dimensions. So we don't do that in the same way. Okay, we've learned over the last couple of days how we add vectors together in two dimensions. We draw a vector diagram. Now, the vector diagram is exactly the same way as it's been for us over the last few days. But just in the interest of simplifying the word problems that we're going to see with this, okay, as opposed to just the pictures that usually I drew for you in the other questions, we're going to define two different lines. We're going to make one type of vector a solid line vector and one type of vector a dotted line vector. There will always be two of the solids, and there will always be one of the dotteds. Here's where we're going to make our solid line vectors. If we're aiming in a certain direction or we're heading in a certain direction, we're going to draw that as a solid line vector. The pilot of an airplane, a captain of an airplane, aims the airplane directly north, or the captain of a ship heads north, or the sergeant in the group of soldiers heads west. If we aim or head in a particular direction, we're going to make that a solid line vector. We're going to draw it as a solid line. if the speed in still air, in other words, I don't know how many of you do this, but when I fly on an airplane, I always go to that magazine that's in the front, that's in the pocket ahead of you. And I know Air Canada does this. I'm not sure if WestJet does this or not, but they list the aircraft that they fly. And they list all these statistics, the wingspan, the length of it, the capacity. They also list the airspeed of that airplane, how fast the airplane can move if there's no wind. Okay, sometimes it's around 900 kilometers per hour. If the airspeed of this particular airplane is 800 kilometers per hour, then that means it might go 850 if there's a 50 kilometer per hour wind, or it might go 750 if there's a 50 kilometer per hour wind in the opposite direction. Airspeed simply means how fast it can go if there is no wind. And finally, we're going to make that a solid line vector. Finally, if there is a wind speed, let's say the wind is blowing at 50 kilometers per hour, or the river current as the captain of the ship is trying to cross the river is 5 meters per second to the west. If there's a wind speed or a current, we're going to make that a solid line vector. Basically, solid line vectors are all vectors that contribute to where we actually end up going. They're not where we actually end up going. They contribute to it. Okay? The direction that I aim isn't where I end up going. The direction that the wind is going isn't where I end up going. The direction that the river current is flowing isn't where I end up going. All of those things contribute to where I end up going. Does that make sense? Combined, they cause me to go where I actually go. So solid line vectors contribute to where I go, or where whatever it is that goes. Dotted line vectors, on the other hand, that's where we actually go. The solid line vectors contribute to the dotted line vectors. Or the solid line vectors cause the dotted vectors. In other words, we might aim in a certain direction, but the wind takes us off course. Those two vectors combined, where I aimed and how much the wind was blowing, caused me to actually go in a certain direction. We also make a dotted line vector where we want to go. Let's say we want to fly directly north to Edmonton. Why you'd want to fly to Edmonton, I have no idea. But let's say that we wanted to go to Edmonton. We wanted to fly directly north to Edmonton. Okay? That's going to be a dotted line vector. If it's where we want to go, we're going to say, it's as good as going there. It's as good as if we actually went there. Again, solid line vectors contribute to where we actually go or where we want to go. Ground velocity, the velocity relative to the ground. Okay? Again, we're going to make that a dotted line vector. So if whatever vector you're given in the word problem contributes to where you go, make it solid. If it actually is where you go, then make it a dotted line. All right, let's take a look at an example here and kind of put this into play here and see if we can determine what's solid and what's dotted. The good news is if you can determine what's solid and what's dotted line vectors, these questions are easier than the questions we've been doing. They're vector diagrams, but they're almost always right-angled vector diagrams right off the top. Okay, the trick in these is not getting rid of funny angles usually. The trick in these is just getting your vector diagram drawn in the first place. Then it's easy. The pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour, but there's a wind blowing to the east. Where does the plane actually go? We've got three vectors here. We've got where the pilot of the plane is heading, we've got where the wind is blowing, and then we've got where the plane actually ends up going. This one here, 200 kilometers per hour to the east, to the north. Is that a solid or a dotted line vector? Heads in a particular direction. Do we actually go in that direction, or is that contributing to where we actually go? Yeah, it's a solid line, because we're not going north, right? We're heading north. That contributes to where I go, but it's not where I actually go. So let's draw that as a solid line vector, 200 kilometers per hour. Notice this time we're drawing vector diagrams, though, with velocity vectors instead of displacement vectors. That's okay. Doesn't matter. There's a wind at 50 kilometers per hour to the east. Do we go 50 kilometers per hour to the east, or is that just contributing to where we go, Joe? That's contributing. So what's that, solid or dotted? Solid. Right? If it contributes to where we go, we're going to make it a solid. Let's draw that right here, 50 kilometers per hour. By the way, solid line vectors have to be drawn front to back, right? Drawn a vector diagram, only the resultant vector gets drawn backwards. Okay, and the solid line vectors aren't the resultant. The dotted line vector is the resultant vector. This is where I go. I aim to the north. There's a wind to the east. You guys intuitively know this, right? Where do I end up going? Well, somewhere north and somewhere east. I end up in Lloydminster or something like that. We can find r and theta, right? Where do I actually go? Now, this speed at this angle. R is going to be 200 squared plus 50 squared. Let's make sure you square root that. And then theta is going to be equal to the inverse tan of opposite over adjacent. Opposite is 50, and adjacent is 200. I told you guys. Is this an easier question than you've been doing the last couple of days? Once you get the diagram drawn, I don't think there's any question that it is. Trick here is just getting the picture drawn correctly. Let's figure this out. I get 206 here, or I get 2.1 times, well, let me get 206. We're not worrying about sig figs right now so much. 206 kilometers per hour. So we're aiming at 200, but because of this wind, we actually end up going at 206. Okay, that's not a surprise. Sometimes wind speeds you up and sometimes it slows you down. Let's figure out what this angle is too. I get 14 degrees. 14 degrees, what of what? 14 degrees, what of what? Listen, we went east and we went north, right? So is it north of east or east of north? Who says north of east? Hands up. Who says east of north? Hands up. Hey, you're right. It's east of north. If we follow our vector diagram, it went north first, then it went east, right? It went east after north or east of north. So we aim at 200 to the north. There's a wind of 50 to the east. Where do we end up going? 206 kilometers per hour at 14 degrees east of north. If we wanted to go directly north, would we aim this way? No. No, we'd have to set up our diagram differently, right? Because if we wanted to go north, then the north vector would be our dotted line, not our solid line. Yeah? Yes, yes. That's right, yes. If you didn't hear that, guys, Louis said for the direction, could we put 76 degrees north of east? Would that be correct? Absolutely, it would be correct. Okay, that would just mean that you drew it like this, 50 and then 200. We've said many times before, it doesn't matter what order you add vectors in, right? As long as you make them front to back or head to tail. The resultant vector would still be your dotted line. Theta would end up being 76 degrees, but 76 degrees north of east instead of east of north. It's the exact same answer though, right? Okay, it's like saying, just describing the angle, the direction in two ways, right? You're 1 meter behind Kathleen. You're 1 meter in front of Tara. Which one's right? Which one's right? Both right, right? Both of those correctly describe your position. So we can have two different ways of correctly describing that angle as well, right? Just based on our frame of reference. Good? Okay, let's take a look at number 3, everyone. It says, a boat whose speed in still water is 2.5 meters per second is in a river that's flowing at 1.2 meters per second to the south. What's the velocity of the boat relative to the shore when the boat is headed south, the boat is headed north, the boat is headed number A and B are straightforward questions. Sometimes we turn them into non-straightforward questions. We make them harder than they have to be. But in the end, they're straight one-dimensional stuff that you could have added together in grade 6. Okay? We have a boat in still water that's headed south. That's going to be a solid line vector, 2.5 meters per second to the south. It's headed, right? That's solid line vector because it doesn't actually go at the speed that it's headed at. That only contributes to it. Solid line vectors contribute to dotted line vectors. We have a river that's flowing at 1.2 to the south. That's also a solid line vector. Now, if we draw this as a vector diagram, technically it would look like this. The resultant vector is drawn from start to finish. Okay, we don't need to do a Pythagorean theorem here. We want to find the resultant vector here, 3.7 meters per second to the south. Now, you could have done that in your head. If you got a boat that's heading at 2.5 to the south and there's a river that's going at 1.2 to the south, you know you're going to be going faster, right? 3.7. Question B says, well, this time the boat is going opposite to that. The boat is headed north. So this time we have 2.5 to the north. We have 1.2 to the south. The resultant vector will be drawn from start to finish like this. Well, the resultant vector here is going to be 2.5 plus negative 1.2, which gives us 1.3. And that's going to be to the north. Okay, again, we could have done that one in our head probably. Hey, you guys know this. This is like being on the escalator, right? The escalator is going at 2.5. The escalator is going at 2.5 to the north. You're walking opposite to the way the escalator is moving. Okay, maybe it's that moving walkway, that moving sidewalk at the airport, you know. It's going to the north at 2.5 meters per second. You're walking to the south at 1.2. Okay, you end up going backwards on it. Okay, you end up going opposite to the way that you're actually walking at 1.3 meters per second. Finally, question C. This is the one where we have to do our two-dimensional analysis. This time, the boat is headed west. Boat is headed west. Solid line vector, 2.5 to the west. We have a river current that's flowing to the south. Let's draw it to the south. The dotted line vector, we've made our dotted line vectors the red ones here, right? But whatever. The dotted line vector, or the red vector, whatever you want to call it, is drawn from start to finish. Here we're going to do the Pythagorean Theorem. We're going to getting 2.8 meters per second. But it's not a straight north or south. We've got to find the angle by using the inverse tan function of opposite over adjacent. And we end up getting 26 degrees. Now, what is that? 26 degrees what of what? Yep, south of west, good. First we go south, then we go west, west after south, or, south after west, I should say. So it's south of west. 26 degrees south of west. Luis, I got a feeling you drew this the opposite way. You drew it 1.2, then 2.5. Yeah. Did you? Okay, so you would have gotten, what, 64 degrees west of south? Okay. So if you did it right, you would have got 64 degrees west of south, right? Do you know where you did wrong there? Okay, let me know if you can't figure it out, okay? Okay. Let's skip that one. Let's not do that one. Let's not do that one either. Let's skip a couple examples. You guys are good at this, right? Let's try this one. Let's try this one. The pilot of an airplane wants to go directly north. We want to go directly north at a velocity of 500 kilometers per hour. But there's a wind blowing to the east at 85. Where do we have to aim? You can see that as a pilot or as a captain of a ship, this might be a good skill to have, vector analysis. If you want to end up going right there, but there's a wind blowing you this way, you better know where to aim so that you end up going right there, right? How many of you guys drive? We've all experienced this before, right? Driving down the highway, there's a big Chinook wind blowing in from the west. What do you got to do to your steering wheel? It's like you're aiming way over towards Banff. Okay, you're aiming at some angle towards the mountains, right? Because there's a wind blowing to the east, you have to aim somewhere northwest or southwest to go straight, right? Where do we have to aim here to end up going straight north? At what angle do we have to turn our steering wheel at, basically, to go straight north? We want to go north. That's a solid or dotted line vector. No. That's a dotted line vector. That's where we go. Okay, we'll assume where we want to go is where we end up going. Okay, we're going to make that a dotted line vector. We want to go directly north at 500 kilometers per hour. There's a wind blowing to the east at 85. That's a solid line vector. Where am I going to draw that solid line vector, though? Really, I have four options, right? Option 1, option 2, option 3, option 4. Two of those options will work. Two of them will not work. Let's number them here. 1, 2, 3, 4. Give me one place that I could draw my vector of 85 kilometer per hour wind. Where could I draw? Position 1, 2, 3, or 4? Joe? Is your hand up? No? You have an answer? Could I draw in position 2? Let's delete all the rest of them here. Does that vector diagram work now? Where would I draw my other vector? I'd have to draw it right here, right? Is that a good vector diagram? Solid line vectors have to be drawn front to back. Is that drawn front to back? No, it's drawn front to front, right? Does that work? No. Can't draw it in position 2. Okay, so position 2 is out. What about position 1? Could I draw it there? Let's try that. Does that work? Let's draw my other vector here, okay? Does that vector diagram work? Yes. Position 1 would work. The other one that would work, let's draw the second one over here. The other one that would work is this one, position 4. Because my other vector would be drawn from here to here, which again would be solid line vectors front to back. I'm going to draw it this way, though. I like this one better. Guys, listen. Intuitively, you know this, right? If there's a wind to the east and you want to go to the north, where do you got to aim? Northwest somewhere, right? You have to aim to the west. You're going north. There's a wind blowing across the highway. You don't turn your steering wheel into the with the wind. Okay, you want to go north and the wind is going to the east. You don't turn your steering wheel to the east. You're going to drive off the road. You turn it to the west. You aim opposite to the way the wind is going. Wind is going this way. We aim this way. Okay, we can find this now. Okay, once again, we're finding the resultant vector. Sorry, no, we're not finding the resultant vector this time. We have the resultant vector. It's 500. Okay, the resultant vector is this dotted line vector. We know what it is. It's 500. This time we want to find this vector, the vector at which we have to aim. But we're going to find it the same way because it's the hypotenuse. It's 85 squared plus 500 squared. And theta is equal to the inverse tan of 85 over 500. We get 507 for this one. And for this one, we get 9.6 west of north. So if you got this wind, but yet you want to go at this velocity to the north, now you better be able to go a little faster than that because you have to aim at 507 kilometers per hour, and you have to aim at 9.6 degrees that way towards the west. Does that make sense? Kinda? Okay, I want you to try a couple problems of this. Your homework will be questions on the worksheet number 6 and 7. Notice I've asked you to skip number 5. We'll go back to that one, okay? Let's try number 6 and 7 right now for homework.